year is 1800 BCE, and the great city of Babylon hums with life. Towering above the city is the magnificent ziggurat of Etemenanke, a massive layered pyramid that stretches toward the heavens, a structure so impressive that later generations might mistake it for the Tower of Babel. This city is the center of the ancient world, where scholars, traders, and astronomers gather to push human knowledge forward. In a bustling marketplace, a scribe sits cross-legged, pressing a reed stylus into a clay tablet. His brow furrows. 5 minus 7, he mutters, rubbing his beard. How can you take away more than you have? That doesn't make sense. He glances at a row of sheep outside his stall. You can't have negative sheep. If you had 5 and lost 7, you wouldn't be left with negative 2. You'd just be in trouble. And yet, he does know something. Distance is always positive. Whether counting the length of a road, the height of a wall, or the time between celestial events. One fact remains: distance never goes below 0. As the scribe carves symbols into the clay, he unknowingly plants the first seed of a concept that will take centuries to fully bloom. The idea that a number's value isn't just about direction, it's also about magnitude. 1,000 years pass. The scene shifts to India, 7th century CE. Here, temples rise into the sky, adorned with intricate carvings of gods and mythological beasts. Streets bustle with merchants selling silk, spices, and pearls. This is a land of incredible intellectual breakthroughs in science, medicine, and especially mathematics. Inside a quiet temple, a scholar sits cross-legged on a woven mat, writing equations on a palm leaf manuscript. His name is Brahmagupta, and today he will challenge everything the world knows about numbers. He dips his stylus in ink and writes, "A debt subtracted from 0 is a credit." His students whisper among themselves, "This is a strange idea. Numbers below 0? Until now, numbers have always represented things that exist: coins, goods, land. But Brahmagupta sees further. He writes a set of rules, making it clear: negative numbers are real, and they have their own logic. Not everyone agrees with him. In fact, in Europe, mathematicians will refuse to accept negative numbers for another 1,000 years. But one thing is now certain: if negative numbers exist, then numbers are no longer just greater than or less than 0. They also have direction. And if numbers have direction, someone will soon need a way to talk about their size without worrying about whether they are positive or negative. The year is 1637, and we find ourselves in Paris, France. The city is alive with new ideas. Philosophy, literature, art, and science are flourishing. The streets are filled with merchants, poets, and revolutionaries debating in cafes over steaming cups of coffee. In a dimly lit study, René Descartes leans over his desk, sketching a curious shape on parchment. A V. His new invention, the Cartesian coordinate system, has changed everything. No longer are numbers just symbols on a page. Now they can be seen. He draws a simple equation: y, x, the absolute value of x. The numbers on the left behave normally, moving upward. But the numbers on the right? Something strange happens. The negative values of x flip upward, forming a mirror image. Descartes leans back and smiles. The world now has a way to see absolute value, a mathematical tool that measures distance without caring about direction. The idea first imagined by the Babylonians has finally found its place in modern mathematics. 100 years later, we find ourselves in 18th century Switzerland. The Alps rise like jagged spires, their snow-capped peaks piercing the clouds. Below, nestled in the valleys, are towns filled with clockmakers, scholars, and some of the greatest mathematicians the world has ever known. In a quiet study, a man sits by a fireplace, scribbling equations into a thick book. His name is Leonhard Euler, and he's about to make math a whole lot simpler. He picks up his quill and writes, "The absolute value of x." 2 vertical bars. That's it. No long explanations. No confusion. Just a clean, elegant way to say, "Forget the sign, just tell me how far this number is from 0. He underlines the symbol with satisfaction. It will become one of the most universally recognized notations in mathematics, appearing in everything from algebra to physics to computer science. Absolute value has its symbol. Its journey through history is nearly complete. The scene shifts to modern times. A seismograph needle shakes violently, recording an earthquake. A voice crackles over a radio. Magnitude 6.2. Across the world, a stock market ticker flashes green and red numbers, tracking profits and losses. In a car, a GPS screen calculates the shortest route to a destination using absolute value to measure distance, without caring about direction. Absolute value is everywhere. It shapes the world in ways we rarely think about. It is not just a concept, it is a fundamental truth. No matter where numbers go, no matter what their signs say, one thing remains: magnitude matters. The camera zooms out, revealing a futuristic city skyline filled with holographic graphs and equations. A young mathematician sits at a desk, eyes filled with curiosity, writing a new theorem in a notebook. Absolute value has traveled through time, crossing continents, civilizations, and minds. From the clay tablets of Babylon to the digital screens of today, it has remained a constant, a universal way to measure, calculate, and understand the world. And as we step into the future, one thing is certain: the journey of absolute value is far from over.